In mathematics, and algebraic topology in particular, an Eilenberg-MacLane space is a topological space with a single nontrivial homotopy group. As such, an Eilenberg-MacLane space is a special kind of topological space that can be regarded as a building block for homotopy theory. These spaces are important in many contexts in algebraic topology, including constructions of spaces, computations of homotopy groups of spheres, and definition of cohomology operations. The name is for Samuel Eilenberg and Saunders MacLane, who introduced such spaces in the late 1940s. Let G be a group and N a positive integer. A connected topological space X is called an Eilenberg-MacLane space of type K, if it has nth homotopy group n isomorphic to G and all other homotopy groups trivial. If n greater than 1, then G must be abelian. Such a space exists, is a CW complex, and is unique up to a weak homotopy equivalence. By abuse of language, any such space is often called just K. Examples: the unit circle S1 is a K. The infinite-dimensional complex projective space P infinity is a model of K. This is one of the rare examples of a K admitting a manifold model for n greater than 1. Its cohomology ring is ZX, namely the free polynomial ring on a single two-dimensional generator XH2. The generator can be represented in DIRHAM cohomology by the Fubini study 2 form. An application of K is described as abstract nonsense. The infinite-dimensional real projective space P infinity is a K. The wedge sum of K unit circles is a K for G, the free group on K generators. The complement to any knot in a three-dimensional sphere S3 is of type K. This is called the sphericity of knots, and is a 1957 theorem of Christos Papakyriakopoulos. Some further elementary examples can be constructed from these by using the fact that the product K times K is K. A K can be constructed stage by stage, as a CW complex, starting with a wedge of n spheres, one for each generator of the group G, and adding cells in higher dimensions so as to kill all extra homotopy. Properties of Eilenberg-MacLane spaces. An important property of K is that, for any abelian group G, and any CW complex X, the set X, K, of homotopy classes of maps from X to K is in natural bijection with the nth singular cohomology group Hn of the space X. Thus one says that the K are representing spaces for cohomology with coefficients in G, since there is a distinguished element corresponding to the identity. The above bijection is given by pullback of that element. Another version of this result, due to Peter J. Huber, establishes a bijection with the nth Czech cohomology group when X is Hausdorff and paracompact and G is countable, or when X is Hausdorff, paracompact and compactly generated and G is arbitrary. A further result of Morita establishes a bijection with the nth numerable Czech cohomology group for an arbitrary topological space X and G in arbitrary abelian group. The loop space of an Eilenberg-MacLane space is also an Eilenberg-MacLane space. Omega K equals K. This property implies that Eilenberg-MacLane spaces with various n form an omega spectrum, called Eilenberg-MacLane spectrum. This spectrum corresponds to the standard homology and cohomology theory. It follows from the universal coefficient theorem for cohomology that the Eilenberg-MacLane space is a quasi-functor of the group, that is, for each positive integer if is any homomorphism of abelian groups, then there is a non-empty set satisfying where denotes the homotopy class of a continuous map and every CW complex possesses a Postnikov tower. That is, it is homotopy equivalent to an iterated fibration with fibers the Eilenberg-MacLane spaces. There is a method due to Jean-Pierre Serre which allows one, at least theoretically, to compute homotopy groups of spaces using a spectral sequence for special fibrations with Eilenberg-MacLane spaces for fibers. The cohomology groups of Eilenberg-MacLane spaces can be used to classify all cohomology operations.